mathematicians, welcome back to another video. We are back at exponentiation, and today we are going to derive the, for me, second most important exponentiation rule out there. It has to do with multiplying exponentials with different bases but the same exponent together. See the similarities here, kind of? It's like the reverse rule to the first exponentiation rule, where we multiplied exponentials with the same base but different exponents together. There we had that we just kept our base, it's going to be preserved, but we are going to add our exponents together. This time, let's see what we are going to get when we do this. A to the nth power times b to the nth power. We are going to make use of numbers yet again, and yeah, with just playing around with those numbers and stuff we have learned in the sets of numbers playlist, we will be able to kind of derive a very nice looking rule for, well, problems of this kind. So let us take a look at a certain example. Really doesn't need to be anything difficult. If you're writing a test, okay, if you're sitting in a test situation and you forget like this exponentiation rule, calm down, take a deep breath and just try to see how this works with small numbers. For example, what happens if we multiply 7 squared by 8 squared? Different bases, same exponent. Why not write everything out using the, well, verbal definition of our exponentiation? 7 squared has been nothing but 7 multiplied with itself 2 times. So this is 7 times 7. 8 squared on the other hand is just 8 multiplied with itself 2 times. So times 8 times 8. And now it really doesn't look any spectacular, right? I mean, it's nice and ordered. I mean, we have this here, but what can we do at this point? Well, let us try to look for a common quantity in here. Something that is kind of common between those two. Why not interchange 7 and 8? I mean, we can make use of the commutativity in the real numbers, for example, under multiplication, meaning just interchanging 7 and 8, leaving us with 7 times 8 times 7 times 8. I hope you agree with me that we can do this. I mean, it really doesn't change if you have 7 times 8 apples or 8 times 7 apples. Okay, really doesn't change the deal here. Okay, now we could go for this with just some calculations. I mean, 7 times 8, they are kind of representing the same quantity here, what we are multiplying together. 7 times 8 is 56, and yeah, this is 56 times 56. By the verbal definition of the exponentiation, this is 56 multiplied with itself 2 times, so 56 squared. But the thing is, we would like to write this with respect to 7 and 8 exclusively, because if you are dealing with abstract objects like a and b, you can't really write out a certain number that they are going to evaluate to. They are just going to be a times b and not 56 like in our case. So let us use the associativity here to make our point a bit more clear. 7 times 8 can be put into parentheses. I mean, associativity works for multiplication. We have talked about this before in the sets of numbers playlist on the natural numbers already. Same spiel here. This is just 7 times 8. Meaning what we are doing is we are multiplying 7 times 8 with 7 times 8. So this is 7 times 8 multiplied with itself 2 times. Let us put this into exponentiation formalism, you could say. So this is nothing but parentheses, 7 times 8 squared. Hey, coolio! We have extracted new information from this. So what you can see at the first glance is that our exponent is being preserved and we have placed parentheses. So let's just bring this up here and let's gather one after another what we have gathered thus far. So we are putting parentheses here, and actually our exponent n is going to be preserved. It's not a coincidence. You can try it out with 7 to the 3rd power times 8 to the 3rd power. Also, we had different bases, but those bases are also being preserved. We are just multiplying the bases together in some way. So what we have inside the parentheses is a times b. And there we go. A to the nth power times b to the nth power is nothing but a times b to the nth power. And this is it. And now you can just like generalize this thing. For example, if we take really big numbers, it's really no good writing all of this out. For really big numbers and really huge exponents, you really need this calculation rule, just because you won't be able to write all of this out if you have really big numbers. For example, 26 to the 32th power times 12 to the 32th power times 135 to the 32th power. I mean, Try writing all of this out like this, won't help you. You need stuff like this to really get a hang of it. So what do we have in common here? And it really doesn't matter if you multiply two things together. Here, two exponentials or 3 or 5 or 1200. It's going to be the same procedure just because, well, commutativity and associativity works on multiplication. So let us get at what we have. What we have is some kind of parenthesis here, all right? We have parentheses. Also, our n up here, our common exponent, is 32. Hell, that's cool. And what are the bases? We have 26 times 12, we are multiplying those together, times 135. This is, by the way, my most favorite number, 135. I don't know why, it just is, alright? I always used it in old MMORPGs, FlyFF for example, or Call Online. And this is it basically. Quite easy, right? This one is pretty easy to remember for most students, but it's extremely helpful. I have made use of this fact in a video I have posted yesterday on my main channel. It was like a really nice trigonometric question. So if you want to take a look at that, there's probably a link in the info box or down there at the top of the description. Never mind, just take a look at the second channel, main channel basically. This is the second channel, and subscribe to it. And then, thanks for watching. If you enjoyed this video, please like, subscribe, recommend channel. If you want to support channel a bit more, subscribe to the main channel, subscribe to this channel. Watch the videos till the end. Buy the merch I create. Support the channel on Patreon. Up until the next video, I'm wishing you guys a flammable day. Ciao.